Bonjour from the Notre Dame de Paris. I'm Esmeralda, and today we're going to be talking about confidence intervals. Previously, you may remember we spoke about the normal distribution, z-scores, as well as some measures of dispersion, including standard deviation. Today, we're going to be learning about the sampling distribution and standard error, as well as how to calculate t-scores. Ultimately, this will lead us to the main topic of our conversation, confidence intervals and learning how to calculate them. So while we can never be 100% sure of our findings in experimental psychology, we like to establish certain ranges for which we feel our correct answers will lie. And this range is what we call confidence intervals. So let's get started learning about the sampling distribution so we can see how confidence intervals come into play. Previously, we talked about the normal distribution in which scores fall symmetrically within 3 standard deviations above or below the mean. We also know that in a normal distribution, the mean is equal to 0 and the standard deviations are equal to 1. So now what we're going to do is we're going to take a look at a sampling distribution, or in other words, a representation of data that was collected from a specific sample of a population. If we take a look at this image here on the left-hand side, this is a great representation of what a sampling distribution looks like. In the center, in the very large red circle, we have mu, or the population mean. All the other smaller circles represent sample means from samples that have been taken from this particular population. So ultimately what happens is a researcher will take sample after sample after sample, depending on how large a population is. The larger the population, the more samples the researcher would probably want to take in order to represent all of the participants within that particular population. So if you think about taking the average of sample 1, then taking the average of sample 2, taking the average of sample 3, so on and so forth, ultimately the average of those averages theoretically will lead us to the population mean. So another way to think about it is that the sampling distribution is the average of all of the means, the mean of all of the sample means. And ultimately, by taking several consecutive samples from the same population, we will ultimately arrive at the mean of that parent population. So the larger the size of the sample, the more accurately it will approximate the normal curve. Also, the larger the sample size, the smaller the variability and the smaller the standard deviation. If you remember, when we talked about variance and standard deviation, we learned that if data points are spread far apart from each other, that increases the dispersion of the distribution and also means that the data points are not similar and not close together. Typically, if you're thinking about the findings of a research experiment, or in this case, predicting a population mean from a variety of sample means, having a large standard deviation and a wide dispersion is not going to accurately predict the population mean. So having a smaller standard deviation, having a smaller variance, is in fact desirable when trying to predict a population mean from sample means. We also know that if we have a smaller standard deviation, we also have a smaller chance of error. And remember, when we talk about deviation, deviation means how far a particular score deviates or is different from our mean. If those deviations are smaller, it means that there's less room for error. In a sampling distribution, deviation refers to the distance of the sample mean from the population mean. So if you think back to our previous discussion of deviations, for example, average deviation, when we were calculating average deviation, we were looking for the difference between each score and the mean. And so we would subtract every score minus the mean to find that average deviation. In a sampling distribution, because ultimately our purpose here is to try to identify the population mean, to predict the population mean, because after all, that is the goal of inferential statistics. So in this case, deviation refers to the distance that the sample mean is from the population mean. Ideally, we want that deviation to be very small because we want to say that we could accurately predict a population mean from a variety of our sample means. In other words, what is the difference between the sample mean we calculate and the true population mean? Ultimately, our goal is to collect enough samples to be able to accurately predict the population mean from which we have taken those same samples. So that brings us to the concept of standard error. If you remember, when we were converting raw scores into z-scores, we had a formula in which we subtracted the sample mean from the population mean and we divided by standard deviation. Standard error is almost like a relative of standard deviation, and we will use it in the denominator for calculating our t-scores in a couple slides. So let's imagine that we take multiple samples from a population, and then we take the average of those different samples. When we do that, that will give us the standard error of the mean. So standard error is basically the standard deviation of all of our sample means. Previously, when we were talking about z-scores, we had one score that we were comparing, one sample mean that we were comparing to a population mean and dividing by standard deviation. In a sampling distribution, because we have multiple samples, what we need to do is take the average of those standard deviations, and therefore we are left with what is called the standard error. We use standard error of the mean to account for possibility of making an error when we predict mu, the population mean, from the sample mean. Because we are using inferences and predictions to generalize to a population from data we've collected from samples, we have to account for the possibility of making an error when we are making these predictions of the population based on data from our samples. And standard error helps us mathematically account for that by including it in our formula. So the formula for calculating standard error looks like this. Standard error is equal to the standard deviation divided by the square root of n. So we learned how to calculate standard deviation in our previous discussion on measures of dispersion. If you have forgotten how to do that, I recommend that you rewatch that particular tutorial video, which was led by Dorothy. Once you've calculated your standard deviation, you are then going to divide by the square root of n, and n, of course, represents the number of people we have in our sample. The other concept that we need to learn is called degrees of freedom, or the number of deviations that are free to vary after certain restrictions are placed on data. So when we make predictions about a population based on data from our samples, we have to make an adjustment to our n value, our sample size value, to avoid overestimation. Therefore, in order to calculate degrees of freedom, we are going to use the formula n minus 1. So if n represents the total number of people in our sample, we subtract 1 from that and we are left with degrees of freedom. You may be thinking, what do I need degrees of freedom for? That part is coming up next. Just remember for now, the most important thing you need to know is that degrees of freedom is equal to n minus 1. So keeping that degrees of freedom formula in mind, let's move on to talking about t-scores. So you may recall that when we talked about the normal distribution and the normal curve, we converted raw scores into z-scores. But what happens when those scores are not normally distributed, when they don't fall on a symmetrical distribution? So that is the case when we would calculate a t-score instead of a z-score for data that is not normally distributed. And more often than not, whenever you go ahead and conduct your own research, you will realize that most data that we collect as researchers are not going to be normally distributed. So instead of z-scores, you're probably going to be calculating t-scores as well. So a t-score or a t-value falls in a t-distribution. It is the same idea as a z-score, but with the consideration of a possibility of making an error. So previously, when we talked about the z-score formula, we would divide by the standard deviation. In this case, we're going to have the standard error in our denominator to account for that chance of making an error. So ultimately, the t-value tells us how far a score from the sample is from the mean of the population, but it's giving us this value in standard error units. Similarly to how the z-score was telling us how far a score is from the mean in standard deviation units, the t-score is doing the same thing, but in standard error units, because again, now we're considering the chance of error. So the formula for calculating a t-score looks like this. T is equal to the sample mean minus the population mean divided by the standard error. So again, very similar to what we talked about when we did z-scores. We had the score minus the mean divided by standard deviation. Here again in the numerator, we have a difference. This time our difference is not between a score in the distribution and the mean. Rather, we are looking for the difference between the average of our sample compared to the average of the population from which we took that sample. This difference in the numerator is then going to be divided by the standard error. It is unlikely that the sample means will be exactly equal to the population mean. Therefore, instead of reporting one value for the estimated population mean, we report a range of values, which is going to be called our confidence interval. So that brings us to our next topic, confidence intervals. A confidence interval is a range of values within which we are sure the population mean, which we're trying to predict, actually lies. So again, we can never be 100% sure that our sample mean reflects the population mean exactly. But so how confident can we be? What level of confidence are we going to accept? So typically we accept 95 or 99% confidence. Depending on how critical the particular research question is, depending on how critical this comparison between sample and population is, will determine the level of confidence that you as a researcher want to set for yourself. So for example, if we're going to be 95% confident, that means we're accepting a 5% chance of making a mistake, because the total percent confidence we can have is 100%. That would be perfectly confident. So if we are 95% confident, that means we're willing to be 5% wrong. Similarly, if we're 99% confident, then we're willing to accept 1% chance of making a mistake, or having a probability of 1% chance of error. Imagine that the people of Paris were suffering from some incredible illness, and the doctors were able to select samples from the population, run some tests, and now they're coming up with a cure, a medical remedy for this particular illness. Because they haven't tested the entire population, they're depending on this particular sample to experiment on. So they administer this particular remedy to a particular group of people, aka these samples from the population. If it is something related to health of a population, if it's life or death, if it's something extremely, extremely important, you probably would want to go with the stricter confidence level, which would be 99% confidence, saying you're only willing to accept 1% chance of error. So if this medical remedy will not work, you as a researcher are going to accept only 1% chance of making a mistake. But if your research question is about something that is not so critical, to the well-being of a particular population, perhaps it's a new festival that's going to take place, the Festival of Fools, happening in the square of the Notre Dame. And perhaps there is going to be a variety of different performers. And the performers that sign up are 95% confident that they can improve the mood of their audience and increase their level of happiness. Something like that could be less strict. So you can be 95% confident that these particular acts will make people smile. And on the other hand, you're going to be willing to risk that 5% chance that the acts won't work and that nobody will find them entertaining. So you can see how different types of context, different types of research questions can actually determine and guide a researcher to choose the confidence interval that they would want to select for their particular research question. So how do we calculate these ranges? How do we calculate these confidence intervals? Well, we have two different formulas. One for the 95% confidence interval and one for the 99% confidence interval. The process and the procedure for how to calculate them are the same. It's just that the values that we're going to be looking up are going to slightly differ. So let's look at the first one. For 95% confidence intervals, we're going to take the positive and negative t-value at the 0.05 level. 0.05 level represents the 5% error level that we are willing to accept. Once we get that t-value, which is coming from a special table that I'll show you in just a second, it's going to be multiplied by standard error. Then that product is going to be added to the mean. So if you're thinking to yourself, this kind of resembles that raw score formula that we learned when we were reversing z-scores, you're absolutely right. So for the 99% confidence interval, we take once again the positive and the negative t-value at the 0.01 level this time. 0.01 because it represents the 1% chance of error that we're willing to accept. We multiply that by standard error, and then we add the sample mean. So why do we have positive and negative t-values? Well, because we're referring to both sides of the distribution. When we talk about the range of the confidence intervals, the lower range is the score that appears below the mean, and the upper range is the score that appears above the mean. When we set these confidence intervals for ourselves, we need to make sure that we encompass both sides of the distribution. So whether you're interested in calculating your confidence interval for 95% or 99% confidence, you ultimately need to do the formula 2 times. One with the positive t-value for the upper end of the distribution, and one with the negative t-value for the lower end of the distribution. To calculate the lower interval, we calculate the negative t-value multiplied by standard error plus the mean. Then, to calculate the higher interval, we're going to calculate the positive t-value multiplied by standard error plus the mean. But how do we find this t-value? So let's take a look. When we looked for percentages corresponding to a z-score, if you recall, we used the normal curve or the z-table. Now what we're going to do is use the t-distribution table to find the t-value that we're going to need to plug in to our formula for confidence intervals. So this is an example of what the t-distribution looks like. The column labeled DF is degrees of freedom, or once again, n-1. The other columns represent the probability of possible error. So if you look across the top, you can see 10%, 5%, 2%, and 1%. For our purposes of our confidence intervals, we have set our confidence intervals to 95% and 99%, which means for the 95% confidence interval, we're going to be using the values in the 5% column, because again, that 5% represents the amount of error we're willing to accept. For the 99% confidence interval, we will look in the 1% column because that represents how much error we are willing to accept for 99% confidence interval. So to calculate confidence intervals, we need to use the t-scores corresponding to the proper error level. Imagine we had a data set with 20 data points. So our n is 20, a sample mean of 6, and a standard error of 0.14. So again, as we learn to calculate degrees of freedom, we know that degrees of freedom are n-1. So the first thing you need to do is identify your degrees of freedom. If I had 20 people in my sample, 20 minus 1 gives me 19. Therefore, I have degrees of freedom equal to 19. I'm going to go to the very first column labeled DF, and I'm going to find the number 19. Once I find the number 19, I'm going to slide my finger across to the right to the value in the 5% column. Why am I using the 5% column? Because that is the amount of error that I'm willing to accept for 95% confidence interval. So if I put my finger on number 19 in the degrees of freedom column, I slide it across to the 5% column, and I see that that value is 2.0930. This is the number that I'm going to plug into my confidence interval formula. But remember, 2.0930 positive t, and then take the same number but make it negative to calculate it with the negative t value. So let's plug it into the formula and see what happens. For my upper interval, I'm going to take 2.0930 and multiply by my standard error, which was given to me above, 0.14. After I multiply these together, I am then going to add it to 6, and ultimately the total is 6.29. So my upper interval for my range of confidence is 6.29. Then I'm going to do the same thing with the negative t-value. So the value doesn't change. All you need to do is attach a negative sign to it. And again, the reason we're doing this is to calculate the score that's going to be below the mean to represent the lower interval of our confidence range. So if I plug in these numbers to the formula, I will use negative 2.0930 times 0.14 plus the mean of 6, and I get 5.71. So we can see that 5.71 is below the mean, 6.29 is above the mean, reminder that the mean was 6, so we can be 95% confident that the population mean is at least 5.71 and at most 6.29. So if you notice, as a researcher, I'm not identifying only one number for what I think the population can be because I don't know. I can't actually predict what that specific number will be. So what I do is I predict a range based on my values of where it's very probable that the population mean will be. So in other words, another way to say this is that I'm 95% confident that the population mean is somewhere between 5.71 and 6.29. So let's take a look at how we can do the same thing, but this time for 99% confidence interval. Assuming we know the same information that n is equal to 20, our sample mean is 6, and our standard error is 0.14, we can also calculate the confidence intervals at the 99% level. So the first thing we need to do is identify our degrees of freedom. We've just calculated them and we know our degrees of freedom is equal to 19. So we're going to go back to the DF column. You're going to find 19 in the first column. Once you do, this time you're going to slide your finger to the right until you get to the 1% column. Why 1%? Because 1% is the chance of error that corresponds with 99% confidence. So when we do that, we see that that value is 2.8609. So as the percentage of error decreases, the t-value increases. So let's plug in the new t-value for the 1% level into our formula. For the upper interval, we have 2.8609 times standard error of 0.14 plus the mean of 6, and we get 6.40. We do the same thing with the negative t-value, negative 2.8609 times 0.14 plus 6 gives us 5.60. Therefore, we can be 99% confident that the population mean is at least 5.60 and at most 6.40. Or another way to say this is that we are 99% confident that the population mean lies somewhere between 5.60 and 6.40. So let's go over a couple more examples to make sure that you're really comfortable calculating these confidence intervals. Given that our sample mean is 100, standard deviation is 20, and n is 25, let's find the 99% confidence interval for the population mean. We know that in order to calculate confidence intervals, we need to find upper and lower intervals using the formula negative t times standard error plus the mean and positive t times standard error plus the mean. So we have all of these values given to us except for standard error. Be very careful that you don't confuse standard deviation with standard error. Lowercase s represents standard deviation, so what we need to do is calculate standard error. To calculate standard error, all we need to do is divide the standard deviation by the square root of n. We were told that standard deviation is equal to 20, and we were told that n, the number of data points we have in our sample, is 25. So if we divide 20 by the square root of 25, that's another way of saying 20 divided by 5, we get 4. All right, so now that we've calculated standard error, we can go ahead and move on to the t-table to find the particular value that we need associated with our degrees of freedom. So what are our degrees of freedom? We know the degrees of freedom is equal to n minus 1. In this case, 25 represented our sample size. 25 minus 1 is going to give us 24. So we need to find 24 in the DF column. Pay attention to the fact that this is the 99% confidence interval. So once you've put your finger on 24, you know you're going to need to slide it all the way to the right until you get to the 1% column, because 1% error corresponds with 99% confidence. We find that that value is 2.7969. So that's the value you're going to plug in both positive and negative into your T formula. So the upper interval would be 2.7969 times 4, your standard error, plus 100, and you will get 111.19. Now we do the same thing for the negative T value, and we are left with 88.81. So we can be 99% confident that the population mean falls somewhere between these two values. So what happens if you have a frequency distribution where you have to calculate all of the values on your own from scratch? So the most important thing to remember is what are the values that we need for our confidence interval formula. We know that we need the average of the sample, we need the standard error, and we also need to know the number of people or the number of data points in this particular sample. So let's go ahead and set up our columns that we need to find those values. Because we have frequency, we know that we're going to have an f of x column. When we add up the f of x column, we're going to divide the sum of the f of x column by n to calculate our average. So let's go ahead and do that. Once you multiply each score by its frequency, this is what you should have in your f of x column. The next thing we need to do is calculate the x squared column. Why? Because the x squared column is what we need to calculate our standard deviation. And if you need to revisit that particular formula, please go ahead and rewatch that measures of dispersion lecture. So x squared means that we're going to take each score and multiply it by itself. So once you do that with all of the scores, you should be left with something like this. The last thing we need to do is multiply each squared x value by the frequency. So ultimately, you're going to take the values that are in the x squared column and multiply by f. And once you do that, these are the values that you should be left with. So the last thing we need to do is get the sums, the totals, for all of these columns. We know that if we get the sum of the f column, we will find our n value. We will see how many data points we have in our sample. If we add up f of x, we will get the sum of f of x column, and we need to add up the sum of f of x squared column as well. So once we do that, these are the values that we should get. N is equal to 25, the sum of f of x is equal to 585, and the sum of f of x squared is equal to 14,413. So now let's start calculating our mean and standard deviation. So if we start with the mean, we can see that the sum of f of x divided by n is our formula for calculating the average. The sum of f of x in this case is 585. Our n, sample size, is 25, so we are left with an average of 23.4. Let's move on to standard deviation. As a reminder, the standard deviation formula is the square root of the variance formula. So standard deviation is equal to the square root of the sum of f of x squared minus the sum of f of x then squared divided by n all over n minus 1. So here we can see that the sum of f of x squared is the value 14,413. From that, we're going to subtract the sum of f of x, 585, and then square it and divide that product by 25. Once we have the numerator, we're going to divide by 24 because 24 represents n minus 1, the denominator. So if we simplify that, we can see that 14,413 is going to be subtracting 13,689. 13,689 represents 585 squared divided by 25. So that second section in the numerator should equal 13,689. Once we subtract that difference, we are left with 30.17, and we need to take the square root of 30.17. Once we do that, we see that our standard deviation is 5.49. But remember, for our formula for confidence interval, we're not interested in standard deviation, we are interested in standard error. So we need to take one more step and calculate standard error from standard deviation. So the formula for standard error is standard deviation divided by the square root of n. If our standard deviation was 5.49 and our n is 25, we are going to divide 5.49 by 5, and we are left with 1.10. So our standard error is 1.10. Looks like we have all of our values to find our confidence intervals. So to calculate the confidence interval, we need to use the t-scores, once again, to find the corresponding value at the appropriate error level. So we know that our sample mean is 23.4, the total number of data points we have is 25, and our standard error is 1.10. So again, degrees of freedom is n minus 1. 25 minus 1 leaves us with degrees of freedom of 24. So we're interested in calculating the 95% confidence interval. So after you put your finger on degrees of freedom 24, you are going to slide it across to the 5% column because 5% error corresponds with 95% confidence. We see that that value is 2.0639. We are going to plug that value both in its positive and negative form into our confidence interval formula. So 2.0639 multiplied by our standard error value of 1.10 plus the mean of 23.4, and we are left with 25.67. We do that with the negative t-value, we multiply by standard error, and we add the mean, and we are left with 21.13. So we can say that we are 95% confident that the population mean falls somewhere between a score as low as 21.13 and as high as 25.67. Let's try this one more time with 99% confidence interval. So again, the procedure is the same. Our degrees of freedom are still 24. The only difference is now we need to find the value at the 1% level because 1% error corresponds with 99% confidence. So put your finger on 24 in degrees of freedom, slide it all the way to the right under the 1% category, and you see that that value is 2.7969. We're going to take positive 2.7969, multiply it by our standard error of 1.10, plus our mean of 23.4, and we are left with 26.48. We do the same thing with the negative t-value, negative 2.7969. We multiply it by 1.10, and we add the mean of 23.4, and we are left with 20.32. So now we are 99% confident that the population mean is at least 20.32, and at most 26.48. Great job, everyone! That concludes our discussion about the sampling distribution and confidence intervals. Thank you so much for watching. Please drop some comments below if you have any questions about the material presented in this lecture, and I hope to see you very soon on another episode of Once Upon a Lecture. Au revoir!